So we will start with some problems, and after a while we will start taking doubts from the current week assignments, and we will see where we can face some difficulties. So first question, I hope you would be able to see. Okay. So uh, please read the question carefully and let me know your opinion about this problem, how to proceed with such kind of problems. And it has another part as well, which is related to this problem. We need to find out the power factor as well as power consumed by the load. Okay. Just by seeing, can you tell me the output power that can be consumed by the load? That is just one step solution. In this problem, we can assume that it is a lossless converter, or there are no losses occurring in between during the transmission from input to output. We can assume that there are no losses. Whatever the power that is generated from the input, that is going directly to the output. Okay. So anything in your mind? 250 watt. Yeah, that's excellent. Exactly, 250 watt would be the correct answer. Okay. So did you would you bother to explain it?
No, sir.
Hello. Yeah, Muthu. You may also speak. Yeah.
I just came. I don't know what you're asking.
Okay, okay. So let me repeat my question. In this question, you just need to explain how to compute output power, or what will be the power consumed by the load if this kind of supply we will have. So
You
from
mean that
just the, yeah,
the fun,
yeah,
it is a product of fundamental voltage RMS into current RMS into cos of the angle between fundamental.
yeah, that angle is fundamental power factor. That would be 60 degree, right?
Yes, sir.
Yeah, yeah, that's correct. So this much was just required for the question number two. Now we need to find out the power factor, and if nothing is mentioned, then you need to compute total power factor. Means whatever the power factor that input will see. So on that, let me write. So input power factor is generally either, if you have read earlier about fundamental power factor, displacement factor, or something, or distortion factor. So I am going to write it, distortion factor into fundamental power factor. Yeah. So why distortion factor is coming out in picture? Any idea about why distortion factor is coming out in the picture?
Because the current is not sinusoidal, it will
Yeah,
reduce the power factor further. So
definitely. Yes, that's correct. Yeah. So see, if we have something else waveform which is different from a pure sinusoidal waveform, then we will have to get some distortion factor, right? And that much factor would be definitely less than one. and it will further deteriorate the input power factor. So input power factor would be definitely less than your fundamental power factor. So first we will see what is the input power factor from the power perspective. So we just now agreed on that our output power will be V naught I naught, that will be V in fundamental. This is one that is denoting that fundamental into I in fundamental into cos phi 1. It means whatever the fundamental power, that is pure sinusoidal power generated from the input side, that will go to the output side if we can ignore the losses. And since nothing is mentioned about the load, so we can ignore the losses in between. And if first let us compute the output power, okay, and that will be computed from this formula because we do not know output voltage or output current. So V in 1 would be your 100 since it is pure sine. And yeah, don't forget to take RMS. Okay, so V in fundamental RMS would be 100 by root 2 into I in 1. So since we are dealing with just fundamental component, so we have to take only first term. We are only bothered with fundamental of current. Why? Because if you compute the power with consideration of all the components, let me write the general expression of power, that is 1 by time period, okay, from 0 to t dt it into dt. So if you multiply both the terms of current and voltage, so first multiplication will occur between these two components, second multiplication will occur between these components, and so on. Right? So you see that if you try to multiply sine omega t and sine 3 omega t components, you will get zero, right? You just try by yourself at your own and you verify it. And this happens because the orthogonal property of sine functions or any sinusoidal kind of waveforms or expressions. So that's about it. And I in 1, that is 10 by root 2 into cos phi 1, that fundamental factor is 60 degree. So I will have to take cos 60, and that will come out to be 1000 by 2 into cos 60 is half again. So it will be 250 watt, as you might have guessed it already. So that was pretty straightforward. And now since we obtained the active power, okay, and we know the relationship between power factor and active power is active power divided by apparent power. So now in apparent power, we have to consider all the terms which constitutes the current as well as voltage. Since voltage has only one component, so total voltage RMS value would be 100 by root 2 volt. And if you try to find out the total RMS current, right, that would be the apparent power VRMS into IRMS. So IRMS, you have to sum all the components, that is 10 by root 2 square plus another term is 2 by root 2 square, and the final term is 5. So 5 by root 2 square. And now if you compute it, you will get 100 by 250 plus 4 by 2 2 plus 25 by 2, that is 12.5. So that is 62.5, 64.5. Is it correct? Mm, yeah, it seems to be correct. And now just you need to multiply it, apparent power, that is denoted by generally S. So VRMS is 100 by root 2 into IRMS is 64.5. Please calculate it for me. So
Sir, 567.89.
566,
67, sir.
567.89
Yes, sir.
volt ampere. Thanks a lot. So that would be your apparent power, and your real power was 250 watts. So now we have everything to compute total power factor or input power factor. So that is 250 by 567.89, that you will get roughly about 0.44, I guess. So this much is your power factor from input side. Okay. So if you need to cater the 250 watt kind of load, you will need that much rating of supply. So that is huge since your power factor is not good. It is really bad power factor, and it is a huge issue in power converters. For catering such a load, you need to design and you need to over design the converter. So that is a issue that you should look for. So that's the drawback of this kind of thing. Okay. So, and let me tell you another way. While I was discussing distortion factors, so let me tell you a bit about distortion factors. So it is generally represented by G, and that is, since our current is distorted, so we have to take fundamental RMS, that is the ratio of fundamental RMS by total RMS current. So fundamental RMS was 10 by root 2 and divided by, we computed current RMS, that is 64.5.
8
This,
point.
sorry, can you repeat that?
No,
8
sir.
point?
Yes. No, no. The root of 64.75 is root 8.03 on the denominator.
Okay, 8.03. And this one would be 5 root 2, so 5 into 1.41,
0.88.
0.88. So, yeah, so this much would be your distortion factor, and to get your power factor again, you just need to multiply 0.88 into your fundamental power factor was cos 60, that would be 1 by 2. So again, you will land up to 0.44. Okay, so uh, in this thing, your fundamental power factor was already poor, that was half, and your distortion factor is 0.88, so you are getting 0.44. Any doubt in this problem? So your answer would be 0.44. So I see no doubt, so I think, yeah, harmonics. Okay, so let us move ahead with some another problem. Okay. In meantime, you can look on current week assignment, and in meantime, in between also we can discuss if you have any doubts related to current assignment. However, I think after solving previous year's assignment, lot of your doubts should be cleared. Anyway, so take a look on this circuit, please. And in this circuit, we need to compute average value of V1, average value of V1 and V2. Yeah. So all the diodes can be considered as an ideal diode. Okay. Mm, yeah. So we will move ahead with step by step. So our supply is sinusoidal. Okay. And for average value, let me write the expression of V average is equal to 1 by time period in one time period, okay, V dt, or you can write it as 1 by omega t for the time period t into t omega t. So during the positive half cycle, right? In one first positive half cycle, some diodes will be turned on, and that will create a circuit. And during negative half cycles, some other diodes will be turned on, and some diodes remain turned off. So we will have to look for both the things, and we can get the answer. So during positive half cycle, let us assume D1, D2, D3. So during positive half cycle, which diodes will be turned on?
D1.
D1, yeah, correct. So D1 only will be turned on during that cycle, and we will have to draw an equivalent circuit. So we will have a supply and we will have a resistor, and both resistors have the same resistance R, R plus V1 plus V2. Let us assume it supplies VT. So if you apply a KVL, let us assume this kind of polarity, you apply a KVL, so you will get VT is equal to V1 plus V2. Okay. And since both the resistance value is same and current, since all the resistance are connected in series, so both the drops would be equal, right? So I can conveniently write V1 is equal to V2 is equal to Vt by 2 during positive half cycle only. Okay. What will happen during the negative half cycle? Which diodes will be on and which will be off?
D3 and D2.
D3 and D2 will be on during the negative half cycle, and D1 will be turned off. Right, that's correct. That's perfectly correct. So again, I will redraw the circuit. So have a supply, and since D3 is on, so it will be short circuited, right? And R, R. Now kindly let me know what will be the value of V1 and V2 in terms of VT.
pi by 2.
V1 would be V by 2 and V2 would be
V, 2
V2
be
would
0,
be
negativity 0.
yeah. Right. So V2 would be 0, right? Since this is short circuited, so here voltage will be 0 and all the voltage will be dropped across this resistor, right? So
Yes.
V1 would be equal to V1 VT, right? Now we have expression of V1 and V2 for a whole cycle, right? Whole one cycle. So now we can compute. So whatever the average value of V1, that would be same as average value of VT. So for 2 pi period from 0 to pi, it will be, sorry, since it is equal to Vt, you can take safely 0 to 2 pi. The supply was pi sine 100 pi t d omega t. Cos 0 minus, I will take pi outside, pi by 2 pi, and if you integrate this, you will get cos 2 minus cos omega into t. So that would be omega t cos 2. Correct? Okay. Hmm.
So this negative side we have to go.
Yeah, yeah, that negative should come. So from pi to this thing, it will be pi into sin omega naught t, pi to 2 pi will be minus pi.
Minus pi sine omega.
Yes, that was the thing. And now cos 0 minus cos pi, it will be related with this term. And here minus 1 will be multiplied with cos pi minus cos 2 pi. So that will lead to your minus half. 2 plus minus 5. Yeah, it will lead to minus half. Verify it on your end and let me know, please.
Sir,
Yeah,
sir, the positive side from 0 to pi it should be pi by 2, no?
0
Right?
to pi, which should be pi by 2.
The first term is
Uh-huh.
pi sine omega t
Uh-huh.
because at that time diode is reverse bias. The diode which is parallel to the load is reverse bias.
Uh-huh.
So the voltage will equally divide since both are of
E-
equal.
Correct. So it will be pi by 2. Yeah, since it was V by 2 during this period and it was V during this period. So you have to multiply it with half. Yeah, you correctly pointed out. And so half will be here and 1 will be here. So yeah, so now you can let us verify. So cos 0 would be 1, cos pi would be minus 1. So pi by 2 pi, let me write half. Half into 1 minus minus 1, so plus 1 plus minus 1. Cos pi would be minus 1 and minus cos 2 pi would be 1. So that is half into half into 2 would be 1 plus minus 2 into minus 1 that would be 2 minus 2 in sorry yes minus so it should be minus 2 and minus 1 into half that will be equal to minus half. Now I think it is making sense. Okay. And why
Sir, can you explain how did you get that? Pi by 2? I didn't understand.
yeah just second. So this minus is taken care with sinusoidal, right? So that's why we do not need to here add one another time. Yeah, so I will just repeat what we have done. So see, during positive half cycle, we identified that we identified this circuit, right? You can see this circuit, and since both the resistance values are same, so the drops would be equal across the V1 and V2. And if you apply KVL, Vt is equal to V1 plus V2, and since V1 and V2 is will be same, and that should be equal to the supply. So during positive half cycle, your V1 and V2 will be equal to V by 2. You got till here?
Yes, sir.
Yeah. So during positive half cycle, we concluded that, and during negative half cycle, our diode D3 and D2 was on. So this kind of equivalent circuit we drew, and after this we concluded if you apply KVL here, V1 will be equal to Vt. Okay, so entire drop, whatever you will see, that should be I think minus Vt here. So V1 should be equal to minus Vt, and V2 will be zero since it is short circuited, right? I hope no problem this till this point. And since
Yes.
we have all the information about now V1 and V2, right? So we calculated the average value of V1, that is Vt Vt by 2, right? So Vt by 2 during 0 to pi. Okay, let me write a step. So V1 is equal to Vt by 2 both 0 to pi and minus Vt from pi to 2 pi. We have the expression of Vt, that is pi sine omega naught 2, right? And we are taking average by in a whole time period. So 1 by 2 pi, that is time period. From 0 to pi, it is Vt by 2, and Vt is pi sine omega naught t, right? So pi by 2 came from this Vt by 2. You got this?
Okay, sir.
Huh. And after that, it is minus Vt, right? So let us modify this. So minus Vt from pi to 2 pi, and minus Vt is pi sine omega naught 2. So here we did not take pi by 2 since we have expression V1 is equal to minus Vt, right? After that, so we took pi outside, so it remains with half only. And if you integrate sine omega naught t, you will get minus cos omega naught t, and cos 0 would, you can write initially cos 0 minus cos pi in this fashion. After this, you will have minus Vt, and that is pi. We have already taken pi in common, so it will be minus 1 into again cos pi minus cos 2 pi. So that will lead to your whole thing, and I think some yeah. So pi by 2 pi will come out to half, and half into cos 0 minus cos pi, that will be 2. So total it will be half, and again this minus should be here, and 1 into cos pi minus cos 2 pi. Okay, so cos pi is minus 1 and cos 2 pi is minus 1. So minus 1, it will be minus 2. Okay, minus 2 into 1, that will be minus 2. And I think 1 negative point has come extra. Is there anything we have missed? Should be minus 0.5. So sine integration minus cos pi. Hmm, some calculation error I have committed, I guess. Otherwise, it should come 3, right? Minus 2 into minus 1, 3. So it should be 3 by 2 from the 6.
Yes, sir. It is 3 by 2 only. It is coming, sir.
Yeah, it is 3 by 2 coming. I don't know in answer they have mentioned minus 0.5 how they have mentioned.
Sir, but as per the waveform, it has to be the average has to be negative only for V1.
Yeah, yeah. From V1, yeah, from this logic, we can simply say that VT is more dominant in negative thing, right?
Yes.
VT is for negative cycle and V by 2 is for only positive cycle. So it should be negative. Some calculation mistake has been committed by me. I think I should verify or you just verify at your end. Let us know. I will just take one more try. Pi by 2, yeah, so half minus cos omega t. Let us go step by step. Cos
Sir,
omega t. It
sir,
will
our
just,
starting equation is correct only, no, sir.
yeah, yeah. This everything seems to be correct. I don't know where did I commit. Okay, just let me verify once, and after that we'll be good to go. Minus 5 minus VT. That is correct. Cos minus. Okay, okay, okay. T from pi to 2 pi. Let us calculate this one. Half into minus cos pi minus cos and again minus cos 2 pi minus cos pi this time. So half minus cos pi will be 1 minus plus 1 again half is minus cos 2 pi would be minus 1. Yeah, now it is coming, I guess. Minus cos 2 pi will be minus 1 minus cos pi would be minus plus and cos pi would be minus 1. So it's minus 1. Yeah, now I think it is correct. No. Okay, so I will leave it for you. You just verify, or maybe in next session I will calculate it and present it to you where I did mistake. Sorry about this problem.
What should be the answer, sir?
It should be answer of V1 should be minus zero point 0.5 minus zero point 0.5 as we can easily observe that minus VT is dominant. It is for entire negative half cycle and VT by 2 is for positive half cycle. So answer should be negative. Right? That's why we cannot doubt the answer also. Yeah, so moving ahead with V2, let us see what V2 has. So V2 is existing only for positive half cycle. So V2 is uh, from 0 to pi sine omega t dt omega t half minus cos t from 0 to pi half minus cos pi would be 1 and minus cos 0 would be minus 1. That's 2 by 2. That will be 1. So it is coming 1. So V2 was quite straightforward. Even some ambiguity, I think. Yeah. Okay, anyway, if there will be some time in at the end, we see again. So I think concept should be clear. Some calculation errors can commit sometime. If any doubt in concept, we can take it. Otherwise, we will move ahead. Right. So there are none. So let us discuss a problem related to a thermistor. Right. So what are the properties of thermistor? Anyone can recall from the lectures? And why do we use thermistor first? This should be the first question. Anybody, why should we use thermistor? What are the use of thermistor, particularly in power electronics converters? Yeah, it is negative temperature coefficient. So the primary objective to use thermistor is to limit the inverse current. Okay. So at since it has a negative temperature coefficient, so initially it will offer high resistance to the inverse current so that it would not damage the circuit. And as we proceed towards the steady state, our resistor value will be lower down due to the negative temperature coefficient characteristics, and we will have better performance at the steady state, right? If we will have higher value of resistance at a steady state, then majority of the losses will occur in the component itself rather than to achieve at the output. So that's the purpose of thermistor that was not being fulfilled by the resistor, right? So that's why we moved to the thermistor, and that give us sometimes desirable outcome. So this problem, you read it carefully. I will just turn the light on a while. Yeah, TD, you are correct. Resistance decreases with increment in temperature. So that's why we did not stuck with resistance and we moved ahead with certain components which has negative temperature coefficient. So in this question, we are asked to find out the steady state RMS current in milliamperes. So let me highlight it and add the condition of temperature 80 degrees centigrade. Okay. Yeah. So from this problem, the resistance at, let me, yeah, so temperature at 25 degrees centigrade is 200 ohm and the resistance at 80 degree we need to compute, and we have some characteristics. R2 is equal to R1 into e raised to power b 1 by T2 minus 1 by T1. So we are given with the coefficients. B is equal to 3950, and T2 T1 we know T2 will be 80 degrees centigrade and T1 will be 25 degrees, 80 and 20. Yeah,
Do we use degree Kelvin or degree Celsius here?
yeah. Since it is mentioned already in the problem that in Kelvin, so you should generally proceed it with Kelvin. 25 plus 273, that would be 298, and 273 plus 80, 353. Yeah, so here you should move ahead with Kelvin, I guess. Yeah, as it is stated in the problem that these are in Kelvin, T2 and T1 are in Kelvin, so you have to put Kelvins, right? Otherwise, if it would have mentioned that they are in degree centigrade, then you should have put it in degree centigrade. Okay, so whatever the requirement of the problem, you have to think in that manner. So let us compute R at 80 is equal to R at 25 into e raised to power b, that is 3950, into 1 by 353 minus 1 by 298. And R25 is nothing but 200. So you will get the value of 200 into this much. So you will land up to the final value I am writing. Our the resistance at 80 degrees centigrade, that would be 25.4 ohm. Okay. So we can see that our resistance value has been dropped down from 200 ohm to 25.4 at a steady state. Okay. So that's the advantage. It's 8 times of whatever it was initially. Now our objective is to find the steady state RMS current. Okay. So we do not have any circuit. Now we have to see the problem again, from where we can find out this steady state current. So, hmm, any guess from reading this problem, from where we can extract the value of current by plugging in the parameters in which expression? Hmm. In second part, we have something power given, and we know that power is related to current, right? P will be equal to I RMS square R. Since R we have calculated at 80 degrees centigrade, we can compute power loss, power dissipation of thermistor, right? From this expression, C is given in the problem, right? So we will move ahead with this. Okay. So now again, you might think that it is in centigrade or kelvins. In temperature difference, we can take anything, either degree centigrade or degree Kelvin. However, the C is given in terms of watt per degree centigrade, right? So it is watt per degree centigrade. So if it would not be kind of differentiation thing, then you have to take care. Otherwise, it would be fine. So 11 milliwatt C is 11 milliwatt per degree centigrade, and T2 we know 80 degrees centigrade minus 25 degrees centigrade. Mm.
Kelvin also.
Uh, See here degree centigrade is given for C constant, right?
Okay.
Anyway, if you use Kelvin here, the difference would be same, right? 80 plus something. Let me write it. 80 plus 273. minus 25 plus 2. So that's why I mentioned that in different, wherever differential will be there, it will be cancelled. So it doesn't matter in differential. It
Okay.
will matter wherever we are using absolute values. So it doesn't matter at this stage. And anyway, you try to match the units always. So since degree centigrade in denominator, so you can take degree centigrade, right? 11 into 10 raised to power minus 3 into 80 minus 25, that would be 55, right? So 55, 50, 80, yeah. So it will come out to be 605 milliwatts. So this much power dissipation is occurring at 80 degrees centigrade with that thermistor, right? This is power loss. Now you know power loss is equal to IRMS square into R. Power at 80, have to use I80, and we will get RMS value 605 into 10 raised to power minus 3 divided by R. We computed 25.4 ohm. So it will come out to be, I think I have that value, that will be 154 milliampere. Okay, is this fine? Any issue in this problem? So with thermistor, you will be generally given with two conditions, one at
Okay.
initial temperature, one at final temperature. You just need to put the resistance and you just need to do the desirable things. Problems might be.
What is the final answer, sir?
Final answer is your 154
54
milliampere.
milliampere.
Yeah, that's correct. So I think in current week's assignment also you might see one problem related to hot resistance, cold resistance. So cold resistance is nothing but your initial resistance and hot resistance is the final resistance. And after that you just to conclude.
Do we have an application of thermistors as current inrush current limiting really in practical use, or it just an theoretical one?
No, it is practical, right? Thermistor is practical thing. You can use wherever the desirable application. If you need to have rugged and cost effective, then you can go ahead with thermistor. Otherwise, you can use MOSFET kind of things. Or if you are not worried about power density of your converter, you can go ahead with transformers. Transformers are like really good isolation, but they are bulky. And since generally for rectifier circuit we have 50 hertz of frequency, so at 50 hertz frequency, as we have low frequency, you will have to design a bulky transformer. That volume of transformer will be higher. So that's why thermistor is quite rugged. Yeah, we use in real world.
Thank you.
Yeah, welcome.
Sir, among all these methods, which one is the commonly used, sir, for limiting inrush current?
Yeah, so as I just mentioned that it varies with application to application, right? Where you have a strict cost constraint, then you might use resistance as well, right?
Mm.
You have to trade off with your power loss efficiency and cost. So it varies with application to application how much your project have the fund, right? If you are doing some BTP kind of project or some low level project, you can go ahead with resistance or resistance. But if you have that you can afford that much, then you can go ahead with MOSFET. And if you do not have any worry related to a space or a weight kind of thing or volume kind of thing, you can obviously go ahead with transformers. So that depends on application. and of course, what are your capital costs? So it will vary.
Hello, sir.
Yeah, yeah, please go ahead, Vinay.
So I have a doubt on the peak voltage.
Mhm.
So suppose if we have a 230 volt RMS voltage as an input for a rectifier, so in that case, without any inrush limiting current method, like without anything, so the VM, the peak voltage will be 325.27 volts.
Yes.
Okay. Suppose if we use a resistive method of inrush
Mhm.
protection, so what happens to the drop across that resistance? Because the VM will definitely will get reduced, right? Because of
Yeah, yeah,
that resistance.
yes. So
Okay.
that's not the drawback with resistance. It is really good
Hmm.
in dropping the voltage, right? It will definitely protect your circuit. But the
Hmm.
drawback is as you move to the steady state condition, your resistance value is same. So now again drop is happening the same. Let us assume you take any value. So let us assume your input voltage is 325, right? And your output, so suppose your drop across resistance is happening 150 volt. Okay. So your output will be
325 minus 150 volts.
150. So it would be corresponding to 175 volt, right?
Yes, yes,
So you are applying 325, you are getting 175. That is not fair in like most of the applications at a steady state.
yes,
And on top of that, you will have some finite resistance. Let us assume 1 ohm. So your losses is again 150 square by 1. So that is huge losses. So your efficiency will be again it will be quite low. You have two trade-offs. You are not getting your desirable output voltage, and again you are losing in terms of efficiency. So that's not good for any circuit. It is really good. It has dropped your voltage during inverse period, right? It will limit your current. Whatever the total resistance, it will add on. Let us assume your load has something zero point 0.5 ohm or kind of thing. So it will limit your inverse current by at least three times. But for that, you have to pay in terms of efficiency and losses and your output power. Your output rating will be generally lower because all you can do if you have your output rating is constant or at least desirable what you have applied. So you applied 325, you will not set up for 175 kind of thing. So that's the thing.
So
And
if we have
so
to
in that
calculate,
case,
yeah.
yeah, yeah,
yeah,
go
go
ahead,
ahead,
please.
Sanjay.
So if we had to go ahead with calculating the effective voltage at the output for a full wave rectifier with the capacitor filter, a similar case. So let's say that the resistance is there. Then how would you compute that? Because the capacitor would charge to a different voltage now, right?
Yes,
The
yes,
ripple voltage would be different, swing.
yes, you are correct. So see, now in that case, your capacitor will be in between. Right? So at capacitor, you will see this 175 volt of peak, right? So here you will see peak of 175 volt. So now your supply has been reduced from 325 to 175. So your peak capacitor voltage is itself now 175. So your output voltage will vary from 175 to the ripple. 175 to 175 minus delta V. Right? Why
So
that?
with,
Yeah, yeah.
no, so without the inrush protecting resistor, we
Uh-huh.
had some ripple voltage. Now, would that ripple voltage swing remain the same or it will be different?
Yeah, it will be same since see your drop across the resistance. If your power factor is unity, let us assume your power factor is unity. So whatever drop is happening here, all okay, whatever the current you will have here, I RMS in that drop would also be in phase with this current, right? And whatever the phase difference between your V in and IRMS, that phase difference will be same till this point because resistance is not gonna change your state difference. It will be same, and you will have to consider only IRMS into R, and that will be subtracted directly from your peak voltage for an instantaneous point I am telling. Did
Okay.
that answer your question?
No,
Okay.
maybe because it is a part of the assignment, I don't think we should have that answer immediately. We'll hold for it for next week, I think.
Yeah, yeah, we can hold. Okay, so uh, which part you did not get? At least we can discuss about concepts, right?
Yeah, yes, yes.
So
So
which,
the peak to peak voltage swing
yeah,
or the ripple that we have, would that be the same or not is the question that I am having right now.
that will be same. From my understanding, it will be same.
Okay, okay.
Yeah, Vinay. So you were saying something?
Yes, sir. Anyway, if we use a resistance method for inrush current protection, we
Yes.
should be using a high value of resistance, right?
Uh, See, again, the trade-off. If you will use high
Uh,
value of resistance, your losses and your drop will be higher. However, your protection
mhm.
will be. But see, for protection, you need to compute from the circuit, right? In one question, it must be asked that how much. Or sorry, I will take that kind of problem in later session. That how much resistance should we connect in series with the supply to limit the inverse current, and since we will have some value of inverse current, and from that particular thing we can compute the value of resistance that can be connected in series with the supply. So that we will see in the problem.
Okay,
So
sir. Compared to the resistance method, the thermistor method is better, I believe, compared to the resistance method, right?
yeah, that's definitely that is better, but better things come at some cost, right? So that if
Okay.
you are ready to pay, you definitely you can go ahead with the Mr.
Okay.
So let me take a problem related to kind of thing. Hmm. Here it is. See, this kind of question, what we just discussed, that how much resistance should we connect in the series to limit the inverse current of 5 ampere, right? So we have the limit of inverse current 5 ampere. So for this thing, we can assume we will have to consider the worst case scenario. Let us assume VC has the maximum value of the supply 20 volt. Okay. So let us assume this same voltage peak, we turned on this switch at instant when sine is peak, so at theta is equal to 90 degrees. Now your capacitor will see the voltage 20 volt, right? It will see 20 volt. Now your inverse current would be is given. Your limit of inverse current is given, right? That is 5 ampere. It cannot shown below peak inverse current must be restricted to 5 ampere. Okay. After 5 ampere, you cannot afford, right? For such kind of circuit, you have to design, and you have to design a resistance with the low minimum value such that it can tolerate that much of inverse current, as well as it will have the lesser loss, right? So the minimum value of that resistance would allow that minimal loss is happening to the circuit, as well as at the same time it is protecting your circuit from the inverse current. So that value you have to decide for this resistance. So now can you decide that value, or what will be the value if you can tell?
So it will be peak current, peak voltage minus the peak current.
Peak voltage divided by peak current, you mean
Correct,
to
correct.
say.
Yes, yes.
Yeah, yeah. So that R limit would be V peak divided by I peak. Okay, so if you have the limit of 5 ampere, your peak voltage is 20. Worst case scenario, we are assuming 20 volt and your limit of inverse current is 5 ampere. You want to protect till 5 ampere. After that, you are not bothered. You are asked to design for an inverse current of 5 ampere. After that, it is not your responsibility to answer. So it will
So
be
voltage will be 20 root 2.
voltage will be 20 only because 20 is the peak amplitude here. It is not RMS, right?
Okay, okay. Hmm.
So it will be 4 ohm. So you just need to connect 4 ohm of resistance. That would be your best trade of that kind of scenario. So I think Vinay, you must get your answer. And
Yes, sir.
any doubt for anyone? Yeah. Let us see. I have some other problems. Yeah. Any other doubts related to current week's assignment that we should discuss or we can discuss?
Sir, regarding the efficiency of the
Hmm.
rectifier circuit,
Okay. So
okay,
regarding job,
efficiency the rectifier circuit.
you mean fourth problem or fifth? Because fourth. Yeah.
What, sir? Here, P out by P in would give us an efficiency, no?
Yes. Yes.
A P out we will be calculating by V average square divided by R. We
V
will
RMS square by R. See.
V
So
average.
V average. Yeah. Yeah.
That is
Uh,
how we will calculate also.
yes. In rectifier, output will be DC component, so it will be average. So V not average square divided by R. You can compute, and I think by reading this problem, you can directly compute your output voltage since you have output ripple, right?
Yes,
So average would be maximum plus minimum by 2, and
yes, our
yeah, so output would be and output power would be B naught average square by R, and input
our
anyway you have that V in into I in RMS is given, so everything is given here, I guess.
yes. Like yeah, we that P in
Hmm.
we would be taking the drop across so the power dissipated in the series resistance also into account,
Yes,
no?
yes. Here V in would be shifted from that value, right?
Yes.
That's the thing I think Sanjay discussed that this is the current week's assignment. So this is the thing. Whatever the peak value, that will be just shifted. Since it is resistance, it will be in phase with the your supply, right?
Okay.
So no any uh, difference, no any deflection from your supply phase since it is resistance. So that's the property of resistance. Whatever drop will be there, that will be within phase with the supply. So
Okay.
it will be just shifted and yeah, and this
So I should have a changes in V naught, V output voltage by taking the series
yes,
resistance drop. Okay.
definitely you will have that
Okay.
change of drop across that resistance,
Okay.
right? And that drop if you reduce from your supply voltage and then you have to consider the ripple.
Okay. Okay. And in the input power, I have to add that take that V in and I in would be giving me an input power.
Yes,
PM
yes,
into IM by 2.
Yeah, you are correct. VRMS into IRMS.
This
Yeah.
drop, this I square R also I should I square R loss in 200 ohm should also be taken into account. No?
Yeah, see, you have input. If you have input, now you are having output. So that's fine. That's another approach if you are calculating losses. See,
Oh,
for efficiency, you can write directly P naught by P in,
P
or you can write P naught
P by
by P naught
P
plus.
naught minus loss plus loss.
Yeah. So now wherever losses are occurring, you can find out.
Okay.
So whichever way is convenient to you, or you verify it with both the ways, so that would be better to match the answer, right? So and see this fourth, fifth, and sixth, I guess. No, fourth, fifth problem is given just to visualize the difference between resistance and thermistor. So how much efficiency there with resistance, and in fifth question try to identify the efficiency even though it is not given in the problem. You try to identify with your own and you see the difference between both the problems. Okay? So you compute efficiency with both the things. I think you can easily compute this way P naught and P in directly. And indirectly, you can also compute P naught divided by P naught plus losses. And losses, you will have IRMS square into R, right? So you compute and verify it. Use of
The-
capacitor will. Yeah, yeah. Sanjay, you are saying something?
yeah, the output ripple that we are having is 20 volts. So 230-volt is the mains. So if we
Yes.
had not we ha- if we had omitted the inrush current resistor, then we
Mhm.
could have got 315 at the output, right? Or
Yes.
325 at the output.
Not 325. It would be 3.
Ripple
Okay. The
325
minimum voltage you are talking, right? 325 minus 20 would be minimum voltage.
minimum voltage. Yes. So that would be the ripple there. Right.
That should be the minimum value, and 20 volt is equal. So
Correct.
yes.
Correct.
And even now in present case also 20 volt will be the ripple. Nothing will change in the ripples. And it is clearly mentioned in the problem that output ripple is 20 volt. So you can assume
Right.
even now 20 volt as a ripple.
Right, sir.
Yeah, someone raised their hand, I guess. Sorry, I also. So do you have any other doubts regarding this problem? Or should we move ahead? Use of capacitor will give rise to peaky currents and it will not be desirable. Okay. So yeah, since you have capacitor and capacitor is fulfilling the purpose of having low voltage ripple, right? It comes with its own cost. You have to pay in terms of your inverse current, right? Since your capacitor has very low impedance, and if you see in lecture also, I think professor had mentioned that your omega C will be like less, very less. C is generally in microfarad for low low dense circuit. So yeah, your impedance of capacitor will be really low and almost if you assume almost equal to zero just for a case study and your input has like 230 into root 2 that is 325 and 325 minus 0 divided by uh, you know since your output is not charged, so 325 minus 0 divided by almost 0, so that would be a huge ampere. So yeah, it gives rise to peaky currents and it will not be desirable. But we have to stick to capacitor because of our ripple. And if you do not want to incorporate capacitor in your circuit, then you just need to move ahead with multiples or multi-phase rectifiers. So generally in three-phase rectifiers, your ripples are reduced. So that's another solution, but that's again, it is costly. You will have to put six switches, right? And that will lead to further costs. Did that answer your question, TD? Okay, I hope.
Can you focus on assignment? I mean, question number 5. I'm not able to understand what do you mean by startup voltage.
Okay, okay.
That could be anything, right? It could be
Yeah,
Vmax also.
just let me see this problem. I will bring this first on the screen. So, using a series thermistor, taking this current value during the startup is 5 times of input RMS current. Okay. So, and output ripple voltage value is 5% of the startup voltage drop across the thermistor. Yeah. So see, what does it mean? It means that your output voltage ripple will be 5% of whatever drop I RMS square into R at the startup. So a startup, the resistance value will be cold resistance. So that will be 100. So R cold. So it implied that this much drop into 0.05, that is 5% of a startup voltage drop across the thermistor. You got the thing, Sanjay?
Yeah, I think so. Let me
Yeah,
check.
that's what it states. Anyone with any another doubt in this problem?
In second problem, sir, problem number 2,
Okay, problem number two. Just a minute.
problem number 2, sir.
Yeah, yeah, I'm taking that.
Okay, okay.
So here it is given diode bridge rectifier, metal filter. So here, see, uh, when MOSFET will be on, right?
Yes, sir.
That voltage is required 12 volts,
Yes,
and you are given with the ripple in output voltage, right?
yes,
Huh. So now this peak voltage will come at this node, whatever the peak is, 230. It means 325. So 325 will be here peak, and your ripple is also given, right? So now
yes,
you can,
triple S.
so now you can compute the output voltage, average output voltage, right?
Yes, yes, sir.
And if you know the average output
Output
voltage,
voltage, I
and
can,
you
that
by
will be
volt,
equal to summation of the two voltages, VR1 and VR2.
yes, yes,
Yes.
correct.
Then
So
I have
you
to,
just,
we need to calculate the average output voltage.
yes, yes. First you need to compute average output voltage, and whatever the voltage you required at this node, you just need to apply voltage division rule, right?
Yes.
Yeah, that's it. R1 by R2. And you see, we not, let us assume V R2 is equal to V naught into R2 divided by R1 plus R2. That is the voltage division rule. And by this formula, if you take this in numerator, since you will know this value, this
Yes.
is like
That is
12 volts.
known
Huh.
12 volts.
So R1 plus R2 divided by R2, and that will give you the ratio, right? R1 by R2 plus 1.
Yes.
And that's all you need, right? Is equal to R1 plus R2, R1 by R2 plus 1. This is unknown, so it will turn out in a single variable. Any other doubt?
This is another way of calculating, sir. Yes, sir?
Yeah, 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 yeah.
Okay, this is another method.
What is other way that you have in your mind? Can you explain? Or
Uh,
you may explain it next week, I guess.
okay, sir.
Whatever, if you have multiple ways of solving a single problem, always try to solve it both ways so that you will cross check your method
Uh,
and answer, right? That's always good. Maybe sometimes I may be wrong, so if you verify, you will get proper answer.
See, for the second problem, you have to look at the lower voltage, right? The lower most voltage for flawless operation.
Yes, yes.
You cannot look at the average.
Sorry, lower. What do you mean by lower and average?
Uh, See, the peak is 325. 325 minus 73 is what you should be using, right? You cannot be using the DC value or average value
Okay,
for the
okay.
flawless operation.
Okay, okay. Just yeah, yeah. I think you have a point here. What should be the ratio of R1 by R2 for the flawless operation? Okay, yeah, yeah. I think Sanjay is correct. So for flawless operation, even for the minimum condition of voltage, our this MOSFET should be uh off, I guess, right?
Turn on.
Turned on. No, let me draw it. Have Let us model it with a resistance.
You are right. So at the lower voltage, it should not turn on. And then after the capacitor CG charges, then only it will turn on.
Yes, yes. So initially we do not need this switch to be turned on so that it
Turn
will
on.
offer
Correct.
higher resistance.
So at the lowest voltage also it should work.
Yeah, yeah. That's why we are taking 12 volt. No? After 12 volt, it will be on and our resistance. Yeah. So I think everyone must understand this. You should not take the average value here at output. You should look at since wherever some question has some condition regarding minimum maximum. So at that time, you need to see both the limits, right? So here we we need to specify, right? We need to specify that it should be less than 12 volts, so such that this MOSFET will offer the highest resistance, right? So for that condition, you see both the peaks, both the extreme limits, and whichever is the minimum or maximum, whatever the question is asking, that you need to state in that terms, right? So that's why. Here you should refrain from using average value. That may cost some marks.
Sir, repeat again.
Yeah, so see, uh, during a startup, you need to maintain the maximum value of the resistance of this MOSFET, right? Such that your MOSFET does not get turned on
Turn down.
and it will offer higher resistance during inrush period, right?
Yes,
For that condition, what will be the output voltage? Since you are going to apply voltage division rule, so if this voltage is less, if V out is less, then your VCG or VR2 will be less, right?
yes,
And there will be some instant where your voltage will be less. So
yes,
during the lowest voltage point, if it is not turning on, then it is ensured that at highest value of voltage, it will not turn on. No, sorry, did I say other way around? So uh, if it is not turning on the
or higher
switch
voltage.
at a higher value, it is ensured automatically that it will not turn on at lower value of voltage.
Okay.
So that you will have to.
So here everything is given in steady state condition, no? All the data
No,
are based on steady state.
yeah, see, what do you mean by steady state?
which
There
means
are
that MOSFET started conducting and
uh,
VR2 is at 12 volt.
no. See, the steady state means whatever is happening in a one time period, it is charging and then discharging and again charging and discharging.
It is
Whatever
repeating.
is repeating itself, right? That is a steady state. But what is happening at a startup? Earlier, the inverse, sorry. So earlier, your inverse current was like that, and then it is dying down like that. Means after some interval, right? So this is not a steady state. Now it is into a steady state. So anyway, ripple will be there in the steady state. So you will have to consider the limiting value of voltage. It requires a minimum. So see, it is clearly mentioned that MOSFET requires a minimum gate source voltage of this much to remain in the ohmic region. That is desirable to reduce the power loss of the MOSFET. Right? So in a steady state, your MOSFET will offer a very small RDS resistance, and that is desirable. But at a startup, it should operate in the active region, right? During active region, it will have higher resistance. The profile of resistance will be like that at the startup. In lecture also, professor mentioned this kind of profile of RDS, and this is in saturation at active. So initially, it will offer very high resistance. So that is desirable during our turned on condition, right? Sorry, that is desirable during the startup when inverse current is lowered.
I mean, so you mean to say I should calculate the value, this ratio R1 and R2 at the beginning stage. Here, I should ensure here this point
Yeah,
starts
you
working.
should ensure that it is not turning on the MOSFET and your resistance is
Okay.
not going in saturation.
So
The
data.
ripple, sorry, the ripple voltage is irrelevant here, I think.
Uh, yeah, in that case, you can say that ripple is irrelevant during a startup. Yeah, because it is asking only ratio. Yeah, you can say ripple in the output voltage of the rectifier 73 volt. So yeah, you are ensuring it for the maximum value, so it should not be relevant in that case. So you see this and you apply all the cases what you have in your mind and come out with the accurate answer. I say. So it is a bit tricky problem. You have to apply mind. You have to mess with it. It seems very straightforward in first glance, but after that it has certain layers. So that we should always try to. Yeah. Any other doubt regarding this problem?
Do you have an approach for seven? Maybe I missed it in the start.
Okay, seventh problem. It is quite easy. Uh, you just need to compute equivalent impedance. See, so you need to find out the power factor, right? So Z is nothing but V by I, right? And you will assume we have any zero angle. I have some phi. Let's say generally we take lagging, so phi minus phi. So V by I, magnitude of V, magnitude of I, and phi. You just need to compute this angle phi, right? And to compute, you have to look. This is V in, this is I. Now, the Z equivalent, if you look from this area, that is just combination of series and parallel resistance, inductance, and capacitance. So you write every terms in terms of impedance, and these both are in series, and you have to write in terms of reactances, 1 by omega c and omega l and r. So and you do not forget to use that imaginary component, right? So L is given and frequency must be given. So your this Xc would be 1 by omega c and XL would be, and yeah, it will be j omega c. Do you have any doubts regarding this imaginary components? Have you studied?
No.
No.
Yeah.
So I hope everyone is familiar with the basic circuit analysis. So XL would be j omega L and resistance is generally written as R. No imaginary component. So now you just need to add XL plus XC parallel with this resistance and whole is in series with this resistance, and that expression will lead you to some magnitude and some angle, and that angle will be your power factor angle, right? Because that angle will be, this is nothing but V by I is mod Z and phi. That angle will lead to your power factor angle, right?
Yes, sir.
Yeah. Any other doubts?
Sir, can you explain that imaginary part thing?
Okay, okay. So I will take a circuit, series or parallel circuit. So if you have this kind of circuit and you have RLC, then generally it will be fed with sinusoidal. So let us suppose Vm sin omega t, and current will lag only, that will depend on the circuit. So it is R, it is j omega L, and it is 1 by j omega c. Okay. So for equivalent impedance, if you see from this side, okay, from at this terminal, what you will see, Z equivalent will be R plus j omega L plus 1 by j omega c. J is nothing but a complex number, okay, that is used in circuits to analyze the phasor thing. So J, if you see, that has magnitude of -1. So it is iota of the complex number. Since we have currents in network or circuit kind of thing, so we avoid using iota in terms of I. So we replaced iota with J. So J is nothing but -1 and J square is -1. Okay. And J raised to power 3 is -1 again. Sorry. Uh, J raised to power cube, that is minus j, right? And j raised to power 4 will be equal to 1, right? J cube you can break into j square into j, and j square will be -1, and -1 into j will be minus j. And similarly, j raised to power 4 will be j square into j square, and j square is -1. So -1 into -1 will be 1. So that's the basic property of iota. And if you try to find out the magnitude and angle of this impedance. So you can write R plus. You have to segregate real terms. This is real, and these both are imaginary. So omega L plus, or sorry, minus. You have you have taken J already in common, right? So now you can write uh, J into J square, right? So if you take J common, so 1 minus 1 by omega. See how I manipulated. I needed one j in common, so I have to multiply one j at denominator, and j square will come out to be minus 1, so omega l minus omega.
So
And
hypothetically, if JL and minus 1 by omega c are equal, then we'll just have R, right?
yeah, that's the resonance condition generally. So when this is called as resonance condition or resonance frequency, at any frequency, if you tune certain frequency wherever you are getting omega L is equal to omega C, that will lead to omega is equal to under root 1 by LC. That condition in last session we discussed diode with LC oscillation. So this is your resonance frequency. At this frequency, all your imaginary components will die down and you will left with only real components. And in that case, your power factor will be unity, right?
But if you have this combination in parallel with R,
Huh, that,
then in that
uh,
case,
in that case also I will explain after this one. So just for this case, I will tell you how to compute magnitude. I know you already know just for the completeness. So equivalent, if you need this amplitude of impedance, so you can write real term ka square plus imaginary term square. So it will give you the angle, sorry, magnitude. Now you need the angle which will give you the power factor. So that power factor, so with this expression only, you can directly compute the angle. How? Uh, See, generally resistance lie on x-axis and impedance, right? This x generally called XL minus XC, and this is your total impedance, right? So this angle you will find out whatever is your power factor angle. So this is your R, and now so you have this expression. This phi will be tan phi, right? So tan phi will be equal to XL minus XC divided by R. So this power factor angle you just need tan inverse with this value. Now, if your XL is higher than XC, then you will lie in first quadrant. If you can see from the graph, so this is your first quadrant, and your circuit is inductive. Inductive means you will have to deal with lagging power factor. If your XC is higher than XL, if your XC is higher than XL, it means capacitor. It means the circuit nature is capacitive. Sorry, I think some, yeah. So your circuit will be capacitive, and it means your impedance will lie in your fourth quadrant, this side, right? It will be in this side since your XC will be higher than XL, and your phi will be negative. So if your phi is negative, it means your power factor is now leading. Leading means we always take voltage as a reference, and whenever we are saying leading, it means current is leading with voltage. Current leads voltage. Always. This is the reference. Okay. So this was for your series combination. Any doubt in this series combination thing?
no,
Okay.
no, no.
Okay, great. So we will move ahead with parallel combination. So we have a voltage source which will supply certain currents. So now in parallel, you recall the concepts from 12th class. 1 by Z equivalent will be equal to 1 by Z1 plus 1 by Z2 plus so on. However, the elements are there connected in parallel, right? So Z1 we can write as R, Z2 we can write as J omega L, and Z3 we can write as 1 by J omega C or minus J by omega C. Fine. Now we need to compute this thing, which will be 1 by Z equivalent, 1 by R, sorry, 1 is R plus 1 by J omega L plus 1 by 1 J omega C. So J omega C will go on numerator. So you have now 1 by R plus, again you take J common. So you will have omega C minus 1 by omega L, right? So case has been reversed from your series case. So now your capacitive term will be numerator. This manipulation I did with the same approach. I multiplied J in numerator and denominator, and we land up to this value. So now this is your 1 by Z equivalent. So if you want to write Z equivalent, it will have 1 by 1 by R plus J omega C minus 1. So this will be your Z equivalent for parallel circuit. And if two elements are connected in parallel, then you can directly write Z equivalent is equal to Z1 into Z2 divided by Z1 plus Z2. This is nothing but the simplification of this 1 by Z1 plus 1 by. So this is just simplification and manipulation. So I hope it is clear.
So what you're telling us is that if inductor and capacitor they are in series and they have same values, let's say impedance values, then they will nullify and give us a zero value.
Yes, yes.
Anything in parallel with that, it is irrelevant.
Anything in parallel with that will be irrelevant. You cannot say directly. If something else is in parallel and that is resistive, then that might be irrelevant. That might be. And if something inductive or capacitive is there, then definitely your condition will be.
Correct, 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 correct. But if it's resistive, then it is irrelevant, meaning the resistance
Yeah,
becomes irrelevant.
yeah, yeah.
Thank you.
Sir, what is the
Welcome.
angle for this? And
Yeah. Correct, correct. So angle will be, so you will land up with some certain value, right? X plus jy kind of thing, right? This will be your Z equivalent. Now, if you do, you can simplify it with x minus jy divided by x minus jy, right? So it will lead to x minus jy divided by x square plus y square. Are you following?
yes, sir.
Yeah. So now your magnitude will be nothing but uh, under root x square plus y square, okay, divided by uh, x square divided by x square plus y square plus y square divided by x square plus y square. So it seems one, it may differ from condition to condition. However, your angle tan phi will be real term divided by imaginary term. So the real term is x by x square. Sorry, imaginary term. Tan phi is your imaginary term divided by real term. This is your imaginary term, and this is your real term. This is your triangle. This is your phi. So imaginary by real will be your tan phi. So imaginary term is your y divided by minus y divided by x square plus y square, and divided by real term is x divided by x square plus y square. So these terms will be cancelled. So it will be y minus y by x, and you can write phi is equal to tan inverse minus y by x. What is the point?
Sir, here also lead and lag applies same as series.
Yeah. It is same. If your this angle is negative, then it is leading, or if your angle is positive, then it is lagging.
Okay,
So, but you see one thing, your component, your coefficient of tan inverse, that has been reversed, right? Earlier it was positive, now it is negative. So
yes.
you can observe the difference.
Uh, can we go to assignment 2 maybe and question number 9 there? I don't know.
Okay, assignment 2, question number 9. You got the solution for that, I guess.
I think the solution, they just have given the answer straight away and it's in range. While I have calculated the precise value, I don't know why I got a precise value, but I don't know.
Okay, this last one you are talking about, right? This question related to power loss in the
Yes,
device.
yes. Why could the answer be in the range? And that's what they said, 1.5 to 1.9.
So you did not get in that range?
No, I got a precise answer based upon the waveform that was given there.
Mhm.
I don't know why they gave it the
Uh,
value between the range.
okay, so you have this issue that why they have given this in range, right?
Yes.
Yeah, so see, that might be they might think that someone may omit certain, that minimum value of loss during turn off, during the off condition due to reverse current, ICO. So many might forget to take that in account. Or generally they give range just that to, qualify your answer in that zone. Or sometimes what happens that some other guy is preparing the solution. So they do not know that there must be accurate or precise only solution should be this problem. So they
Yeah.
basically differ the range. So either of the case might occur, but none of them should bother you, I guess.
No, my answer was way off. It was half the value given by them. So that's why I'm just wondering.
Okay, so you got how much for this?
I got 0.875 and the answer is given between 1.5 to 1.9.
Okay, so you got uh, some answer. But you did any mistake? You verified it on your own?
No, I have not verified yet, but I'll just verify it afterwards. I didn't realize that the answer checked assignment is given to me. So I did not check that. I'll check it and then maybe next time when we are going to have a difficulty solving session, I
Yeah,
may
yeah,
inquire on this.
actually, this problem we solved quite 2, 3 times, and some members might have got correctly. So anyone who are able to speak and who has got this correctly, can you speak now, please? Anyone? Anyone has verified this? Yeah, Muthu, go ahead, please.
Sir, I think in this problem, while calculating this ICEO,
Hmm.
uh, This that can be not considered, sir, because even though it is given as 100 micrograms.
But with these values, you got the correct answer.
Yes, sir, we got it.
You got in the range.
Yes, yes.
Yeah. So, Sanjay, you might take on your own once, and then we can discuss
Sure,
anytime.
sure. Yes, sir. Yes.
So, any other doubt related to current week's assignment, or otherwise, I will solve one or two more problems from previous year.
Sir, sir, can you go to the initial portion, what you taught today
Okay.
regarding the perfect?
Regarding the power factor. So, you have any doubt regarding that, or you just want to see that portion?
That portion alone, I want to refer it.
Okay. Otherwise, I will immediately upload the video, so you do not
Okay,
worry.
sir. Okay. Because last week it took almost a day to upload it.
No, no, last week I immediately uploaded within half an hour.
But
Someone emphasized that.
yes, sir, we requested for immediate uploading. But for me, I was checking, but it was on only on the next day,
Okay,
Wednesday.
okay, so just let me go there. Yeah, first question was related to your power factor.
Perfect. Okay.
So just we computed it with two ways. One is to compute output voltage and divide it with input voltage, right? So if there are no losses, then you will get same as fundamental power as output voltage. And other way is to compute distortion factor. So I hope I will definitely upload within half an
Okay.
hour. So you can definitely go
Go
through
through.
it
Okay.
because it will be boring for the other members, I guess. And this thing we are stuck here. You were there in this portion.
Yes,
There
sir.
was
Yesterday we the Saptarishi sir discussed this problem.
Sir,
okay.
actually,
So
that problem uh, for the second term, it has to be plus, sir. This term,
okay, this term here it should be plus.
Yes.
You are
yes.
saying
Either
okay.
this has to be plus or the sine omega to be should be shifted by pi. If you do
Ah,
either one of that,
hmm,
then we
hmm.
can arrive at.
Yeah. So why did we take minus at that time? Okay,
Sir,
so
sir, minus is because of the negative half cycle it is connecting now from pi to 2 pi that voltage V1 is dropped across minus
hmm.
sin omega t. That is the reason you took
Yes,
minus.
yes, because V1 is equal to minus VT. That's why we took
Yes,
minus here.
minus.
Yeah. And if we consider it minus, then it is written correct, right, Muthu?
Sir, if it is minus, then we have to shift this pi sine omega t minus pi because
Hmm. Okay.
because there is no symmetricity on the x-axis. Uh,
Uh,
Actually, we can consider as the addition of two waveforms with pi by 2 omega t sine and pi sine omega t.
okay.
Uh, if you integrate, so if you take that as an addition, pi by 2 sine omega t should be
Okay.
integrated from 0 to pi.
Just let me draw the waveform.
Bottom should be higher.
So this is V1, and your V1 should be half of
B.
this during this period, and it is of this, right?
Negative.
Should be reversed.
Ah, uh,
Negative, sir.
yeah.
Negative.
No.
Because
I guess see
the
V1T is
current.
minus VT, and
Okay.
VT we are not doing anything. We are not interfering with VT, right?
Okay.
So V1 should be minus VT and minus VT, and this portion is minus already during that period.
So the current through that R is in the opposite direction of the previous case. So that I into here
Okay. So
it
you
is
mean to say
first case it is I
yeah,
into
yeah,
R.
yeah, you are
Polarity
correct.
for polarity in that R should be will be different, sir, in both the cases.
Yeah, right. I got it. Thanks a lot. So that's why it was coming. Will be positive. It will be negative. Okay. So now we can write it as plus either this one or minus minus. So here you can write now plus. Yeah. Thanks a lot, guys. If you 2 plus everywhere, so minus 2. Now it is matching now. Yeah, so the thing was, uh, we will discuss it once more. What we did, we considered that current is flowing in the same direction. However, when we are reversing the direction of supply, our current direction will also reverse, right? See, here we assume the same current direction. So that will reverse during the negative half, right? And hence it was coming minus Vt. But minus Vt is not exactly negative because it will be, minus IR. Minus Vt will be equal to IR, and I had been reversed, so it will be minus IR. So, there was this question was twisted a bit, and if you are segregating two time periods or time periods in two segments rather, so that would give us the better idea. See, we just confused with it, but I think now it is clear. So, any doubt in this again? We can go through this once more if you ask. We were doing mistake that we were not reversing the direction of current, we were just reversing the direction of voltage. So that's why we got interchanged value of our voltage during the negative half cycle. So that's what the all trouble lied. Okay, so in last 5 minutes, I think I can take one more problem.
Sir, where is it put on the website where the YouTube links will be provided for the difficulty solving sessions, or
Uh, See,
where do we find it?
for that thing, one seat might have been shared with all of you who are registered with this course. Furthermore, I also shared the link of that YouTube channel, which is mine. So I think you do not have that channel, so I will just cut copy paste that link of that channel. For time being, you can access from there. Otherwise, I think it has been given to all of you. So you just copy this link with you somewhere, and you can access through this channel. Yeah. So any final doubt before we can wind up the session? I think now it is enough, and you should not have any trouble in solving current week's assignment because last three problem I can see, last four problem, that is quite straightforward. Just based on power factor, that is the easiest thing if you have even once gone through the basic circuit theory. and the first six problems are related to just your inverse current. You just need to apply appropriate value of resistance. You will not get in any trouble. Apart from the question number two, which has really some concepts you need to apply. Question number two, you have to think a bit. You just give it a thought. And anyway, deadline is first March. So you have 3 days. So you just see this problem. And anyway, we have discussed it up to the maximum extent. So now it should not be any trouble. So I think we are good to go and we should wind up now. Thank you all for attending the session. We will meet again next week.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.